Okay. All right. So today we want to talk about something called a single displacement reaction. Single displacement reactions are important. They're just not exciting. Single displacement reactions, they do take place fairly quickly. So when we do our experiment, we should be able to see the effects fairly quickly, but they are not energetic. So they happen, we can see them, but they tend not to have a lot of heat or light or energy associated with them, right? We know that that's a piece of evidence for a chemical reaction: heat, light, and energy. We saw those examples yesterday. But single displacement reactions don't tend to have a lot of heat, light, or energy given off. So they're not exciting, but we do often see new solids being formed, like a precipitate. That's what that means, a new solid is formed. And often we see color changes because they do involve that. So let's talk about what a single displacement reaction is. It's very straightforward. You don't need to rewrite. You don't need to rewrite single displacement. If you've got it once from the head slide, you just need to write the bullets there. It involves the reaction of an element with a compound. So remember, an element is an atom by itself, represented by my A right there. A compound are two atoms together. So you can see there, I've got an element and a compound. In the end, the element displaces an element from the compound. They trade positions. We call it displacing it. So after the one element displaces another element, one element is set free and a new compound is formed. Many teachers will describe this as if someone is cutting into a dance. Now, the way people dance these days, the way you crazy children dance these days, does anybody slow dance? Josh, you do a lot of slow dancing with the ladies? No? Does anybody slow dance at a dance anymore? You know, the good old, you know. Yeah, that's right, because you wobble back and forth. Anyway, way back in the day, not even in my day, that's the way it would work too in the 80s. We danced like that in the 80s. But let's maybe go back to the 50s, where people did proper dancing, if that makes any sense. You know, the saying would be, if a gentleman wanted to dance with a particular lady who was already dancing with someone, they would tap them on the shoulder and they'd say, "May I cut in?" Right? I don't know if it ever ended nicely. I have no idea. But the saying is, "May I cut in?" And I suppose if the other gentleman was much smaller than the bigger gentleman, they might say, "Okay," and get out of the way. And then there'd be a new partner. So that's kind of the way you can think of this particular reaction. Not that that happens anymore, right? Right, Josh? Like I said, do you cut in on a lot of dances? "Excuse me, may I cut in?" Very politely. Did you? Excellent. See, Josh knows exactly what I'm talking about. So here we've got element A. That might be that one particular person that's going to cut in. There's the compound, already two atoms joined together. Atom A politely asks atom B, "May I cut in?" And we have a displacement. Yep. If A is a metal, it will displace the first one. You can have displacement reactions where it's a non-metal displacing the second one, but we're not going to deal with that in this course. So in our course, yes, it's always going to displace the first one. Yes, it is. Okay? Now, in the experiment we're going to do today, we're going to do a bunch of mixtures of metals with compounds. And just like in a dance, some of them will displace and some of them won't displace. You can imagine that if someone's dancing with his best girl, I guess if I'm going to use 50s terminology, and someone comes along, like Josh, and says, may I cut in? That guy might say, no way, man, beat it, get out of here. And the displacement doesn't happen, okay? So not all displacement reactions happen. Some do and some don't. And that's what we want to look at today. In the examples we're going to do, we're going to assume the displacement always takes place. But in our experiment, we're going to see that some happen and others don't. And it means that some metals are very active. They successfully displace. And some metals are not very active. They don't successfully displace. So we're going to look at that in our experiment. Let's do a couple of examples here just to talk about this and show what's happening. So if I have some magnesium and I put it with some hydrogen chloride, the magnesium displaces that first thing. Now the hydrogen is by itself, and we now have magnesium chloride, a successful displacement. Okay? So in this case, the magnesium took the place of, what did it take the place of? The magnesium took the place of the hydrogen. Oops, hydrogen. I'm struggling with my spelling. I had to squeeze an O in there. The magnesium displaced the one at the front, and we just traded positions. All right, just like a dancer stepping in and a new pair of dancers. All right? I do have a little video of that, but it's not very exciting, and I do want to get to the experiment. All it does is when you put some acid in there, it bubbles, because the hydrogen is a gas, and it bubbles away, and you get the hydrogen coming out. And then the magnesium eventually disappears, because it's being reacted away. All right? Here's an example of a chemical reaction. What is Zn? It's zinc. HCl is also hydrogen chloride. Again, that's an acid. You'll notice here in the chemical reaction, the Zn picks out the H. It results in ZnCl2, and that's because we had to cross over the charges, just like we do when we find the formula for any compound. And it turns out that the formula for hydrogen that's a gas is H2. There's two little atoms stuck together so that it turns it into a gas. Again, in this case, what did the zinc take the place of? What did it displace? Which atom was displaced in there? Tyson, what do you think? Which atom did zinc displace to get into that position? It kicked out the hydrogen. So again, it displaced the H. Again, a video of that looks very similar to the video of the magnesium. So I don't want to do it. I want to get to the lab so that you guys can do some actual ones. Okay, you guys must be up ahead. So let's do two examples here. Oh, double displacement is for Monday. So this is the end of my note. These last two examples are the end of my note, and then we will do the experiment. So if we took some copper metal and we put it in a solution of silver nitrate, and the compound is always dissolved in solution. They're always dissolved in water. You can see our droppers there. They always contain solutions with the chemicals in it. They're going to contain our compounds. I've got 3 little tiny beakers on the back shelf that contain some magnesium, some copper, and some zinc. Those are going to be our elements. So you always have the solid element, a piece of copper. I actually use copper wire that I've clipped into little pieces. This is a solution. So we drop the little piece or we cover it with some solution, and we then wait and see if a reaction happens. What's the displacement? What's copper going to displace? Yep. So what is the copper going to be with? Copper, nitrate, and what's left all on its own? Silver. So all you have to do is trade the appropriate people in order to get these right. What are my products going to be over here? I don't care which one first, whether you give me the element or whether you give me the compound. It doesn't matter what order they go in. What is one of the products going to be of this? Lucas, what do you think? Iron chloride. Iron chloride. And what's going to be left? Just copper. Okay, just copper. All right, so at this point, I'm going to stop my video like I always do, and then we will roll on.